All right. So today we'll continue on the discussion from last Thursday. Can someone remind me what did we talk about last Thursday? DRAM, right? Uh, so we talked about DRAM, but there are a few elements of DRAM that we haven't really talked about. One of them is reliability, right? We actually said that DRAM it consists of capacitor, right? So what does capacitor have anything to do with reliability? It stores charges, right? It does store data in the format of 1 and 0. And it stores charge. Anyone has the dash cam in their car or your parents' car that has a capacitor? So some of them will be lithium ion based, some of them will be capacitor based. What happened to the ones that are capacitor based? When you turn off the car, how long can it last after you turn off the car? It needs to be connected to the car, right? For a short time. It will be available for just a short period of time. And then right after it will power down. Anyone wondering why is that the case versus the other ones that use lithium ion, which by the way, capacitor actually has much higher, well, slightly higher temperature limit. So it can endure like Thailand, basically climate more, right? But lithium ion is a battery, basically. Capacitor is a capacitor, it stores charges. And the reason why you power off, basically everything would power off eventually in a really, really quick manner is capacitor lose charges. So over time, you will notice, well, I mean, at least with the dash cam, you notice the capacitor would like, uh, would actually slowly leaking electrons out, right? Uh, And to some extent, yes, capacitor can deliver different voltage output depending on how much you charge them, right? So if you think about that, right? And also gain charge really fast. So if you think about it, right? Uh, what does it mean if my capacitor in DRAM lose charges? Do I lose the data or what happened to my data? In what way? So I lost the data in what way? So if I refer to the same pointer, let's say I have a pointer value, right? And I refer to the same pointer, will I be able to get the value? Give me 1 second. I think I have a delivery guy coming in. สวัสดีครับ All right. So you're not losing the address, right? The data get what? Let's say it's 1. Let's say that it's full of charge. It's a value 1. After some point, electron drains out. Yes, data becomes 0. So what happened? Let's assume we do nothing about it, right? Let's we assume we do nothing about it. What would happen if I say opening up an image and that image is in your memory right now? What would happen to the image? The color changes, right? You flip one of the bit from 1 to 0. What if it's a significant bit that represents 128? Once back to 0, basically you just subtract 128 from that value, right? So your data become corrupt, right? So this is one of the things that could go wrong. Does it actually happen? So is your computer behaving that way at all? No, right? In a really, really rare case, right? Hopefully not. So it means that there's definitely some mechanism in DRAM to actually guard against that. Uh, to be honest, the topic we're gonna cover today about the reliability is something a little bit more advanced than the typical like com architecture class for the undergrad. But how big is your DRAM these days? And by the way, Justin, that is also correct. You can have like cosmic radiation that have gamma particle that hit that capacitor and then basically excited the state of the electron leak charges and things like that happen too. So you have 8 to 16 gigabyte going into the future, you might have even more. So it means that your capacitor is going to be smaller and smaller and smaller. So what does it mean if my capacitor becomes smaller? How is electron has does electron has a size? It does have a size, right? So it means that if my capacitor becomes smaller, what does it mean? I'm gonna be able to hold fewer electrons, so it's gonna be more prone to failure, right? So there can be error in DRAM cell. Capacitor lose charge over time, right? There's also faults, right? Faults means that, well, somehow electron either move in or move out randomly. Well, it's not totally random. There are cause of faults. Sometimes it's just your capacitor is damaged. It's gone. That cell is gone, right? So these are faults. And let's look at the part where DRAM loses charges over time first, right? So charge basically, if you go back to this diagram again, right? How DRAM operate. Charge leaks to the capacitor. So let's say you finish and you pre-charge. Now your capacitor at full charge, right? You see that from this picture, number 5, to number 1. Actually, we do nothing. We do nothing. But if you look at the picture, what happened to my cell capacitor? It drops a bit, right? Your voltage dropped a bit. So does it ever get filled up? If you look at this diagram, any steps here that fill up the voltage again? So first of all, if we access and we pre-charge, that gets filled up, right? From here to here, you see the capacitor get filled up. So what can we do? What can we do? Anyone want to take a guess? What is the correct thing to do here? Not buffering, but what if I say this? If I know that within say 100 milliseconds, my capacitor would drop the value by half, can I send a pre-charge command to refill the charge? Right? So we can do that. We can just say, hey, I'm gonna pre-charge. I'm not reading anything. I just want to pre-charge because I want to make sure I retain the value of my capacitor, right? This process is called DRAM refresh. What does refresh mean? In a typical computer term, whenever it says refresh, what does it do? It's kind of like reloading, right? Reset, right? So what happened in your DRAM is once in a while, your controller, remember our old friend memory controller from Thursday? It basically send the command, oh, read that, pre-charge, activate, read that address, change to this address, read the other address. It would send the command to refresh. There's also a timing for that. TREFI, refresh interval. Basically, it means that this is the time that I'm gonna make sure that every single cell would get refreshed. How do we refresh? It's almost exact same thing as doing pre-charge, right? You use sense amplifier to make sure charge come back up. So this process is called DRAM refresh. And remember from our diagram, when we pre-charge, can we use the row buffer? If we cannot use the row buffer, what does it mean? Can I read or write to DRAM? So yes, there's a question on the chat that says, is the refresh basically a read and write loop? Almost like that, but we're not literally reading or writing anything. We bring the row to row buffer and write it back to make sure we recharge, make sure electrons move into the cell. Or if it's empty already, it just leave it empty, right? So if you have to do refresh, DRAM becomes busy. You cannot read, you cannot write, right? So when I mentioned earlier that how big is your DRAM these days? 8 to 16 gigabytes. What if in the future you have 64 gigabytes of DRAM? How much more time you're gonna have to spend on refresh? Right? So if you consider this, actually there's already multiple research paper on this topic because starting around year, I would say 2012, 2013, we don't have a DRAM that big yet, right? Back in 2012, well, how big is your DRAM? 4 to 8 gigabytes. So you're gonna spend a little bit of time doing refresh, right? These days it's 8 to 16 gigabytes. So back in the day, we there was including the research group that I graduated from CMU, we do a lot of memory research. And we kind of found that, hey, this is gonna be a big problem if you have 8, 16, 24, 32 gigabyte of DRAM. Why? Because you can spend so much time, like say 30% of the time refresh, right? So what can we do? Right? What can we do? So we can reduce the overhead of DRAM refresh. I'm gonna talk a little bit about some high level overview, right? The first problem is, let me ask you this: do we have to do refresh every single row at once, or can I just do maybe 1 or 3 or 5 rows at the same time? So you don't have to, right? So there are multiple ideas that have been thrown around. Some of the industry, actually, I think most industry actually use some of these techniques or combination of these techniques to reduce the overhead of refresh. For example, we can refresh in small bursts, right? Instead of refreshing the entire DRAM at the same time. I'm going to space out my refresh so that every single row get refreshed every 64 microsecond, right? And we do a few rows at a time. We can do that, right? So the benefit here is basically it's allow you to uh, space out the refresh so that when you have to read or write, you don't get blocked, right? You don't get blocked by the 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 refresh interval, right? By the way, I think this microsecond sounds wrong. I think it should be 64 milliseconds, right? So I might got that bit wrong. Sorry about that. If I remember correctly, it should be 64 milliseconds, right? And this is called auto refresh. Basically, it's just making sure that groups of row it is gonna be group, like emphasis on group of rows, not the entire DRAM, will be refreshed automatically at the same time. Right. So that's it about refresh. That's it about DRAM leaking charges, right? So this is some of the things that I want to mention today because in the future you might have fancy DRAM with huge capacitor. So look at TIFI and see how that might impact your system. Sometimes most of the time you are not going to feel any effects. We as a hardware designer is going to make sure you never feel that effect, but sometimes it might come and happen, right? It might happen. The other thing, you definitely can feel the effects. DRAM error. What does it mean? Sometimes when you read DRAM, you get wrong value, right? The thing is, you can try to detect and try to retrieve correct value. This is called ECC DRAM, Error Correction Code DRAM. We are not going to go into the theoretical, I guess the maths behind how this is done. There's actual like provable maps that say, okay, with each of the encryption algorithm, how many bits you can tolerate. Like, can you tolerate 5 bits that are becoming erroneous and you can correct it? Or can you detect 6 bits? If there's an up to 6-bit error, you will say, hey, something is wrong, blue screen, reboot. So this can happen. Why is this important? Let's say you graduate. Let's say by some good merit that you did, you own a company. And let's say you have a need to buy a server, right? Let's say you need to buy a server. You say, hey, I need to buy a server with certain memory. And you say, hey, you need this thing called ECC DRAM. And it costs more because it definitely will cost more. It's error correction code DRAM. So now you know what they are. Basically, it's error correction. With the technology these days, you are able to deal with about 5 bits of error, 6 bits of detection. So if you have up to 6 bits, you can detect that something is wrong. If you have up to 5 bits, you can correct it back. Right. So this is really effective to be used as a server grade DRAM. Right. So that's why I want to bring this up. There's also multiple types of fault. Some of them you can ignore. Some of them you might not be able to ignore. Hard error means that the cell is actually broken. So error will become permanent. This is called permanent faults. If you use memcheck and it report certain number of faults, if it's permanent faults, consider maybe it might be a time to buy new DRAM, because just think of it as capacitor die. Like, you can't do anything with it, actually die. Soft error is not permanent. We call this transient fault. And as Justin said earlier on the chat, well, you can have cosmic ray coming in, literally hitting that capacitor, bumping electron. Right? So this thing can happen. Sometimes charge leaks out and you miss, like, the refresh interval doesn't really do anything to that, because maybe, for example, the temperature go up. Right? When temperature go up, it affects how much error you're gonna see. So this external factor can cause soft error. So this is treatable to some extent, right? Basically make sure that, well, if it's cosmic ray, pray that you don't get hit by gamma and beta particles. If it's temperature, maybe cool down the machine, things like that, right? There's also multiple ways to correct error. The main idea is we're gonna add more bits to detect and correct error. The most basic thing that I would recommend you to check a Wikipedia articles. We will not have time to cover this today. It's called Hamming code. Hamming code allow you to do 1-bit error correction, 2-bit error detection. We call it SecDet. SecDet is 1-bit error correction, 2-bit error detection. So it can detect up to 2 bits. ECC DRAM that you can find nowadays can go to 5 to 6 bits error, right? So these are from many of the DRAM manufacturer that you can buy, both from Micron, Samsung, SK Hynix. They also have the ECC option for DRAM. There are also many other techniques. Are we gonna do the error correction within the rank, or within the cell, within the row, right? So these are the options from the hardware manufacturer. All right, so we are kind of done with the error part, right? So let's move on to the next topic of the memory, which is, hey, let's push DRAM toward this limit, right? Anyone here heard about the term overclocking? I guess another thing that you might run into in the future. Hey, I am poor. I don't want to buy a new machine. Let me overclock. So DRAM timing, the time it takes to read, write, and activate and pre-charge, those are configurable. To some extent, it can be configured, right? So what would happen if I change, for example, the timing? Anyone want to take a guess? What if I just say, hey, the timing for a pre-charge command would shrink, make it lower? Well, depends on the power, the whole like power and energy consumption, right? It might not, actually, it might not. But let me go back to this diagram that I showed earlier. This one. Between step 3 to 4, you're pre-charge. You're basically trying to pre-charge, right? What if I say I'm gonna spend less time over there? What could happen? Yeah, you might not ended up with enough charge in the cell, right? So your refresh interval, which is 64 milliseconds, is not long, it's not frequent enough, right? So you might have error. So let me go back to our earlier the slides that I show about the pushing the RAM to word limits. There are some ideas that have been proposed around as well, because the cell, they're not equal. What do I mean by that? These are variation when you manufacture a chip, right? Anyone know how does Intel come up with the i5, i3, and i9, i7? Or what would be the idea that makes sense? Yes. So you are right. So let's say I'm gonna fabricate a chip, right? I'm gonna use the design and then I'm gonna test how good is that chip once it's come out. If it can meet the check mark for say i7, I'm gonna mark it as i7. If I cannot clock it as fast as the i7, I'm gonna say, hey, it's i5 with this particular clock speed. And then i3, I'm gonna disable certain things to make sure the chip runs fine. This is called process variation. Process variation is basically when you manufacture a chip, you can have the high quality ones, like a perfect chip, and then the middle of the pack, the average chip, and then the bad ones, right? To make sure you can sell everything, you're just gonna label them as a different generation, well, different tier for the chip, right? So the same thing happened to DRAM, right? So there may be region that say, hey, this region can be clocked really fast. This region can be clocked slower. So some idea, for example, well, you can overclock DRAM for sure, right? You can overclock DRAM, be more aggressive, have more frequency, higher frequency. So hopefully, you don't see the effects of this error. Or you can selectively oversupply DRAM for a certain region, right? You can also make DRAM consume less power. Why is that gonna be beneficial at all? If I have less power, it's gonna be DRAM is gonna be slower. What particular type of devices would benefit from using less power or less energy? Embedded system. Anyone here use a laptop? What is the limited resource on a laptop? Battery, right? So if you look at the spec sheet of laptop DRAM, you might have seen it's actually said this. LPDDR. Anyone well, if you always plug in, probably I can suggest, I can guess that maybe your batteries die too quickly in most this scenario, right? Yeah, so all the GPU on mobile, like many of the modern day computer requires a battery, right? Anyone want to take a guess what LP stand for? So if you look at DRAM's memory, low power, yes, it's low power DRAM. What do they do? We actually feed less input power. It actually does consume less power. So your machine would last longer. Right? So these are these different things that you might see in the market these days that ECC DRAM, LPDDR DRAM. Now hopefully you know what they mean, right? Hopefully now you know what they mean. The benefit is you can make DRAM more reliable. You can make DRAM consume less power. What else? What are other memory technology? Again, this is anything here forward. will not be on the exam. I want you to know that they exist because, again, let's say you're rich, you own a company, you want to buy a server, and you want to buy, hey, what will I look forward to in the next 5 to 10 years, right? Emerging technology can replace or complement DRAM. A graphic cards nowadays comes with these two things. 2D tile DRAM. So instead of having this chip in a stick memory DIMM, right? I would make sure you call it DIMM. That stick that you buy, right? That are not actually physically attached next to each other. You can actually tile them next to each other so that they can have much higher bandwidth. 3D stack DRAM. Basically put the chip on top of next each of the chip. Like put it on top. What's the benefit of putting things on top of each other rather than next to each other? Less space, right? You have more room. It takes a lot less area. What else? Look at the pin. Is the pin on my DIMM one-dimensional? Basically, the pin would go from left to right, right? If you buy the DIMM, right, from left to right, one-dimensional. Also, I guess electron doesn't have to travel that far. If I have a 3D or like 3D thing for my DRAM, what happened to the surface that connects to the CPU? It becomes two-dimensional, right? What's the benefit of having the pin that connect to the CPU one-dimensional versus two-dimensional? You have much higher bandwidth. So with 3D stack DRAM, you're gonna get a lot more bandwidth as well. This is called high bandwidth memory or HBM. You might have seen the terminology before. It's called HBM. Imagine the DRAM chip that is on top of each other, right? So these are HBM technology. There's also this thing called non-volatile memory, right? We'll talk about non-volatile memory in a bit, but let's talk about the 3D stack DRAM. So basically, this is multiple layer of DRAM chip. You put one on top of each other. Benefit, higher capacity, right? AMD GPU has it. NVIDIA GPU these days, they have it too. The slide is a little bit old, so I need to update that. Sorry about that. When you connect each of the layer, what happened is you have to connect them physically. We call these metal that go from one layer to another. Like there's going to be a piece of metal that poke through the layer, right? There's multiple of them. We call this through silicon via. What does metal do to a circuit diagram? It's a conductor, right? It allows electron to move around. It's metal. If you stick a piece of metal in an electrical outlet, what happens? And don't do that, guys. But it allows electron to move through, right? So through silicon via allows charges to move through so that you can read from it, process the data. It offers a lot of internal bandwidth. It's also offer a lot of external bandwidth. Your one-dimensional pin that connect to the motherboard becomes two-dimensional. Yay, right? What's the difference between capacity and capacity? It's the same thing. I might have misspelled that. I'm sorry. It can make things higher in capacity given the same area. You can even put some crazy things. I can put processor on DRAM. Now I have the CPU connects to a DRAM, but the DRAM has its own tiny computer on it. This is something called processing in memory. This is another technology. That you can, well, these days people are proposing we can do processing in memory. For example, I have a collaborative work with a research group at CMU and ETH Zurich that would perform DNA sequence alignment within DRAM. Basically, you have this logic that do sequence alignment so that you don't have to transfer data between memory, cache, the CPU. You have this processor stick to DRAM. Data transfers just on in within DRAM, right? We can get tens and hundreds of times faster, right, than current solution. The paper is published last year. So these are the new cool thing that might become available in the future. You can probably also have compute elements within the package of processing in memory again, right? Uh, all right. Any question about 3D stack DRAM? This is something that in the future, 5 to 10 years, you might see. It's already there for the GPU. GPU already is utilizing this, but you might see a fancier and fancier version of this in the market. So this is one of the things that is an image. I can show you actually. Do you mind if I show the quick image of the design? Not the actual image, but the let me see if I can. So logically, it looks something like this. You have like chip on top of chip on top of chip, and there's a true silicon vias that connects things. Right? So hopefully this is making things more clear. It's gonna look something like this, essentially. Much higher bandwidth, much better connection, much more internal bandwidth. And then let me talk about my own work that we published earlier. Yeah, it's a DRAM condo. It was really great. Well, a DRAM condo with multiple elevator. So this is the design that we so sorry about going through the paper. Wait, where is that figure? Here. So this thing is embedded to the logic layer of the last layer of DRAM. So these are actual logic that perform the tasks that we want to do. In this case, it's basically sequence alignment. What is sequence alignment? When you want to sequence your own DNA, right? It's a bunch of ACTG, 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 and a bunch of those, like millions and millions of those base pair. You want to construct them so that you can get your own DNA. So you know if there's any likelihood of getting cancer or anything, any mutation, any weird mutation that you've seen. Sequence alignment basically is one of the process to put these shorter bursts of like base pair DNA, base pair inside your own DNA together so you can reconstruct your own DNA. So yeah, this is some of the things that become possible, I guess. Right now is theoretically it's possible. We have a paper on it. We did some evaluation. We were kind of working with Intel on the project. And who knows, right? In the future, maybe it would evolve into something that you can actually see as a product. But it's probably likely far in the future, like at least a few more years. All right, so now we talk about things that need refresh. Let's talk about something that doesn't need refresh, right? So what if I replace the capacitor with something else? If I replace the capacitor with something else that doesn't need a recharge, what does it mean? It means that my value, the value inside my memory will not ever gone away, right? Well, yes, obviously it's gonna consume less electricity. That's one of the benefits of non-volatile memory. You don't need to worry about leaking. So let me ask you this question: that what happened if you turn off the machine? It's not gone. Charts are not leaking. It's gonna be still be there, right? So what is the benefit of that? Actually, no one knows. What do we do with it, right? Because there's a double-edged sword. Let me actually open up this discussion. if I know that my data is still gonna be in the NVM DIMM, non-volatile memory DIMM, if someone steal my computer, what would happen? It's the data is still there, right? So they can see everything stored on a DRAM NVM DIMM, right? So it's kind of nice if you have data there. When you boot the computer again, you can restore from where you are. You don't even have to. Maybe you don't even have to boot, right? The boot sequence would be a lot faster. Like, oh, that's the state of your computer. Done. Yay. But at the same time, if someone steal that data, I see all pieces of data. Maybe I can reconstructing again, and I know your password, right? How do I prevent against that? But okay, let's discuss non-volatile memory a little bit. Essentially, the technology is this: cells are not based on capacitor anymore. Charge no longer leaks over time. It no longer leaks over time. What does it mean? It means I don't need to refresh. Typically, they're also denser than DRAM. What does it mean? Within the same area, I can fit more things in. It means that you now can have an option of terabytes of memory. Is that nice? It's nice, right? So you don't need to refresh, and this applies to most non-volatile memory. There are also some proposal that use certain types of material where you still can refresh. If you refresh at certain interval, this memory is going to behave faster. It's going to behave almost like a cache, right? It's going to have much lower access latency than SSD. SSD is also non-volatile storage. The concept is similar. You store the data there, it stays there. Benefit is now you have a storage, as someone suggests on the chat, which I forgot who said that. I'm sorry, guys. It's already like way up in the chat. Is this like more like having an SD card as your DRAM? Yes, and it's fast, right? So in our future, so this is a great question. Are we gonna look forward to terabytes of like almost cache-like speed? Who knows? Actually, I've been looking into certain material with students at ETH Zurich as well on a new basically new type of devices that integrate the CPU. But basically, it's like a monolithic CPU with memory on the same package, which means the memory becomes really fast, right? So who knows how we're gonna architect that? Maybe we have to change. Well, I mean, we are trying to re-architect that and see how to make the computer even faster. Who knows what you ended up with, right? So this is kind of exciting time to be an architect. There's so many new materials, so many new hardware, so much demand from the software. Uh, will the CPU be bigger? Also depends. Because if you have a big CPU, it also means you have to control temperature. You don't want to grill meat on your phone or fried eggs or yeah, you know what I mean, right? So these package size it does matter to power and temperature. Power and temperature also have something to do with the lifetime of the device as well, right? Imagine if you have to sit outside all the time instead of sitting in my air conditioned room, right? You probably might like die faster. um, right? Because this increase in temperature would destroy material faster as well. What's the benefit of non-volatile memory? Treat it as a fast, really fast, but much smaller SSD, right? There's also new Intel, like for example, Intel Optane line of products also is trying to push non-volatile memory so that you can actually have this as an option as the cache between DRAM and your storage. So it's a fast DRAM. Slower than DRAM, but much higher in capacity. So another great question. So with non-volatile memory, what would happen to DRAM? There was actually quite a lot of debate, and it's still ongoing on what do we do? Why? Because Non-volatile memory also have reliability problem. You don't have to refresh, but if you write to it too much, it dies. Why does it die? A lot of these operations, when you write to it, you shock them. Imagine you get electrical shock every time you need to update your data, right? You're gonna die. So this is what happened to non-volatile memory. What are the other downside? Typically they are slower than DRAM. They are typically slower than DRAM. So we will replace DRAM depends on the technology. If the technology improve, what do you mean by like buffer overflow? Okay, I'll wait for your explanation while I'm babbling on. Uh, so it depends. There's also a proposal to have DRAM in parallel with NVM so that we can use DRAM for fasting, NVM on floating. There's also a proposal to use DRAM as a cache for NVM, right? One of them would work in parallel, DRAM and VM. Fasting go here, floating go here. The other proposal is DRAM is a cache to NVM. Everything go through DRAM. If you don't have data in DRAM, you check the NVM. So there's many other, like many things that we can do. So that's not buffer overflow, but yes, if you write too much, it dies. Uh, it's a property of the material, basically. It's like the SSD. SSD, if you write it too many times, it actually dies as well. So what's the benefit? Larger memory capacity, data is persistent. You don't need to refresh. So you can use it as a form again. And another thing that you can do is maybe you can use this as a data recovery. What if machine go down or something happen? You need to revert to the earlier state, right? You can use NVM for that. It's a way to recover data in case something goes wrong. Recover so that you can resume execution. Why is that going to be beneficial? Let's say you're running a huge deep learning server right now, and you're training for 5 days already, and then somehow small power outage, and you haven't finished training. Would it be good to have something that would allow you to store the intermediate steps, right? So you can rerun, right? So you can hopefully rerun and continue from in the middle of the training and things like that. It doesn't. Hopefully, it's no leakage power. So generally, you're gonna have lower power consumption. NVM can also use in combination with DRAM. As I said, you can have DRAM in parallel with NVM, DRAM as a cache to NVM, 3D Crosspoint, which is a product from Intel these days that you can buy. I think they discontinued that and they're gonna basically architect it in a different way. But that device works by having DRAM as a cache to NVM, and you have a control over what you're gonna do with DRAM, right? So these are hopefully you're excited about this because these are the new technology that's gonna come out really soon. Some of these are already coming out. Some of these are going to come out in the near future. By near future, it's definitely something like within 10 years. Why is that the case? We have a much higher demand on memory. A lot of the application nowadays working with terabytes of data, right? You don't have to. I mean, look at this. I asked you to do matrix multiply for project 3, right? What would happen if I asked you to do multiply 1 million by 1 million? How big would the memory have to be? Will that fit in the memory? No, right? That's 1 million by 1 million. I mean, so yeah, so if you look forward, you're gonna have, it's likely that you might need more data, right? Well, I mean, there are different ways that you can compress the metrics into a different format. So you can do matrix multiply, but at the same time, they're gonna consume memory, right? Okay, any questions about the first half of the class that talks about memory? Because I'm gonna move to the second topic. We will do a quick break in the middle so that we can resume around 3 o'clock. And let's talk about what else can we do to actually hide the fact that memory is slow. All right, so if you have questions, feel free to type in the chat. Otherwise, let's take a quick 10 minutes break so we can switch from the first topic to the second topic. And let me tell you this. After we're done with this topic, I actually have nothing else for the material for the class. So in the next lecture on Thursday, I will pick something that might be interesting for you. Maybe like multiprocessor or like how does each of the like how does TPU works, and we do some review. All right. So let's do a quick 10 minutes break. I'm gonna go get coffee. I'll be right back. Really, really high on caffeine, so I will likely talk faster. Sorry, bear with me. When is the quiz again? Likely next Tuesday. Tuesdays, 2 o'clock. You will have probably 30 hours to work on it. I will design to make sure you don't use 30 hours. And this time is likely to not involve programming part. So it would be a lot of written exercise, written question. Should be relatively quick to finish. All right. So next Tuesdays, guys. Anyone that have more than 3 exams next Tuesday, let me know, yell out loud today so I can figure out what to do. All right. Yes, 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 no. Okay, so let's do a quick 10 minutes break. We'll resume at 3 o'clock. All right. And talk about what else can we do. Again, this is the material that will not be on your exam. But what else can we do to deal with memory latency? Because we know that that kills performance. We talk about pipelining. Right? Does pipelining deal with memory latency? There's actually elements in pipelining, but we haven't covered that helps a little bit, but it does not. If you think about it, what we learned so far is if memory take 100 cycle, pipelining will not make that 100 cycle go away, right? Not yet, not yet. And during the time, there's no useful work to be done while you're waiting for the data. And when you access data from the off-shift memory, it's also consume more energy, right? Because you need to send a request over there, send the data back. So we want to avoid it. What's the one thing that we learned to help with like avoiding this latency? Caching, right? Caching is one of the tools that we have. If we have the cache, what if I need to access a certain memory address, but this is the first time I access it? Is that a cache hit or a miss? It's gonna be a miss, right? But let's say this. What if I know for sure I'm gonna access this array? I know for sure that I'm gonna have to access that array. What can I do ahead of time? I can reserve it, right? This is called prefetching. This is called prefetching. Prefetching means I'm gonna go ahead. Because I know that I need address X maybe in the next 1000 cycle. I'm gonna go get it right now so that they're in the cache. This technique is called prefetching. Intel actually has assembly instruction that allow you to prefetch. So it's called prefetch n. Prefetch n, when you change the number from n to the number, it's like prefetch this into level 1 cache or level 2 cache or level 3 cache. Right? Sorry, it's like that moment I want to sneeze, but it doesn't come out. Sorry. The other thing you can do is simultaneous multithreading. We'll talk about this. We'll talk about this in a bit. We're going to cover that. Fine-grained multithreading. Single instruction, multiple data. Single instruction, multiple threads. Combine some of these to do the GPU. All right, so let's talk about prefetching first. So if we can guess what would be my next data load, right? For example, most program written in a predictable fashion. If I have an array, what's the likelihood of my access pattern? How can I know what I'm going to access next? So what's your typical pattern when you have an array? How do you access them? Yeah, word by word, one element at a time, sequentially going up in the index, right? Data next to it, then next to it, then next to it again. So can you predict what address do I need in the future? Can you go beyond spatial locality that, hey, I'm gonna get this first block and hopefully the next 7 word is going to be a hit. Can I say, if I see this, I'm gonna get first block, second block, third block, first block, I'm gonna get everything. I can, right? I can prefetch this. What about the linked list? What about the linked list? How do you access a linked list? A next pointer, right? So if you see this address, it means that the next address is likely to look the same. If you go through the linked list second time, third time, fourth time, right? So it means that when you write a program, there's a likelihood that sometimes you can guess what address you're gonna access next. It means that if we know that, basically, if we know what address are we gonna get next, we can bring them into the cache, right? And I'm gonna go over the simplest one, prefetcher that we call stream prefetcher. Stream prefetcher is a hardware proposal to say, hey, if we know we're gonna access things in an array, why don't we just prefetch them? Because we're gonna need A0, A1, A2, A3, A4, A5, A6, and A7, and A8, then A9, then A10, blah blah blah, right? So if we see, for example, consecutive cache accesses, what can be your guess? If I see cache block 1 and cache block 2 and then cache block 3 that are consecutive, what should be my guess on what cache block do I access next? Yeah, the next cache block, right? So you just go, hey, let me go ahead and get the next one. A different version of this is called stride prefetcher. Let's say I access A0, but instead of A1, A2, and A3, I access A0, A4, A8, A12, A16, right? These come in stride, right? Like what I just showed here. It's a predictable stride. Again, you can use stride prefetcher, right? Similar to almost similar to stream prefetcher, but instead of getting the next block, I would use the strides to predict what I go next. The other technique for linked list, for example, is Markov Prefetcher. So this is Markov model. We're not going to talk too much in detail about this because it's there's a problem about like how are we going to remember what to prefetch. So it is still a few problems with Markov prefetcher. It's not ideal yet, right? Because you have limited memory. You can, let's say you see this address, you know the pointer that comes next is certain other address, right? So you can use a Markov model to predict what are you gonna access next. This has been proposed for a long time, right? Any question on prefetcher before we move on to the next topic? So the next topic is called simultaneous multithreading. Since you've been through the OS class, what is multithreading? What is pthread? Something you don't want to touch again. Yeah. What is a pthread? What does it do? It is the ability to run multiple tasks at the same time, right? Cause of death when you have to code it and it is buggy. Don't die, guys. We passed that point. I don't think you're gonna run into that many issues that are similar from project 1. You might be running into issue that's for project 3, but it's gonna be a different issue. So background on threading, right? Why we only execute one thread of execution because you have limited intermediate resources, right? So What if we maintain multiple contexts and multiple threads of execution? From project one, you know what pthread is, right? From the concept of single cycle architecture and pipelining, how many PC I can have at any given time? The program counter per processor. One, yes, correct. What about the set of register files? Is that because the register files is dependent on each thread, right? Because it belongs to a program. So if you spawn a thread, it need to have its own register files value. R1, R2, RAX, EAX, all those things it ties to the thread. So the single cycle architecture and pipelining design so far, how many set of register can I maintain? I'm not talking about how many registers, I'm talking about how many set one, right? So if I have only one PC, one set of register, one set of pipeline register as well, how many threads I can do at the same time per processor? How many threads I can run concurrently? One, yes. So does it kind of trigger some question mark in your mind right now? So what about multi-threading? The thing that the project wanted I just did. What happened? How can I run multiple things? Does anyone wondering that? Even with thread pool, right? Even with thread pool, let's say I have a thread pool. I have, say, 4 CPU, 1,000 of thread pools. What does thread pool do? Each CPU would run one thread at any given time. Right? You divide the work amongst all the threads. The thread gets launched on the CPU. So what happens if I assign 3 threads to one CPU? What does the OS have to do if I only have one PC, one set of register? Yeah, they will queue up and take turns. So what are the main things that you have to do when you switch between threads? All right, another open-end question. Ever wonder what happened when you have to switch between threads? This process called context switch. Context switch. There's an overhead. Why is there an overhead? Do you have to remember where you are in the program? Do you have to remember what are the intermediate value inside my register? If I have to remember those things, where do I store them? So that's the first overhead, right? You need to actually store them. If I context switch, then do I have to load somewhere the other thread's PC and register files value? Yes. So that's the overhead of context switch. Basically, when you context switch, if you only have one PC, one register files, one set of pipeline register, you have to do the context switch by loading these things either in the cache, eventually in somewhere inside the memory, and load it back, right? So remember, everything has to make sense. Your computer actually run. So when you context switch, something has to remember where we are, right? So let's talk about multiple contexts, right? Each of these run different processes. Again, I am not going to ask this question. We have this question many times, but let's talk about simultaneous multithreading. When the processor is waiting for the memory, right? One thing we can do is we can switch to another thread to keep the pipeline full, right? To keep the pipeline full and to allow concurrent execution of useful work. But if you have one PC, one register files, can you do this quickly enough? So I'm waiting for one load. What happened if I have to context switch? How many loads do I have to generate? A lot, right? Because I need to store PC and to store register files. So any idea what can we do here? Can I add one more PC? I mean, I can add any hardware state, right? So that I can store the second thread's internal data. So hardware multithreading is difference between hardware multithreading and software multithreading. Software multithreading is what we said earlier. I have one PC, one register files. If I have to context switch, I need to generate this read and write request so that I can store what's happening when I run. Hardware multithreading, like Intel hyperthreading, is say, hey, but what if I want to switch between one thread to another in hardware? What can I do? I can add more PC, another copy of register files, another copy of the pipeline register. If I have 2 copies of each, how many threads I can maintain at any given time? 2. How many threads I can run at any given time? Still 1. So it's still 1, and that's okay. Reason why. How many load and store instructions do you see in the assembly code on average? How frequent is that? It's very frequent, right? The thing you run, somehow you need data from an array, from a linked list. So while you're waiting for that data to come back, I'm switching to another thread. Is that okay? Is that going to be faster? Right? It's going to be a lot faster, to be honest, because while I'm waiting for the load, right? While my first thread is not doing anything useful, I'm going to switch right away because I have the PC, I have the register files, resume the second thread. Second thread would run into its own load, switch back, resume the first thread, right? So this technique is called simultaneous multithreading. It's used in CPU everywhere, right? It's used in the CPU world quite a lot. It's not even prefetching the thread. It's already there. Think of it as if the state for both threads are available on the CPU at the same time. But because your whole pipeline is designed to run only one thread, so whatever is available, you run it, right? So what are the trade-offs? Add additional hardware support, right? You need the program, another copy of program counter, another copy of the register file, another copy of the pipeline register, right? Yeah, AMD CPU have that too. This is common, right? There's also a trade-off of like, do I want to switch every time I have the L1 miss? Or do I do it for every L2 misses? Or do I do it every L3 misses, right? So that's another thing to consider. All right, so we're talking about maintaining 2 threads at the same time. The concept of fine-grained multi-threading. Anyone want to take a guess? Wait, what is super thread? I don't think I've heard of it. Actually, I don't think I've heard of super thread. So let's talk about fine-grained multi-threading. Wow. Well, it's actually let me search. Is that something? No, it's not a terminology. Oh, you mean the naming? I don't know. They name it hyperthreading. So what about the next thing, right? If I can maintain 2 threads, can I maintain more? So anyone want to take a guess of what is fine-grained multi-threading? So the idea is when you have a pipeline stall, every time you stall in the pipeline, well, actually it's not for programmer control everything, but every time you stall in the pipeline, you switch to another thread. So let's say I have the pipeline that looks like this. add 1 cycle, multiply take 5. If you access L1 cache, it's 1 cycle. If you have memory access, I can go up to 100 cycle. How many concurrent threads that I need to make sure I never have to stall? Like every time I proceed 1 cycle, I switch to another thread. How many threads do I need? What's the slowest operation here? Memory access. So how many threads do I need to hide all that? I want new thread every single cycle I'm stalling. So how many threads do I need? 100, right? So this is fine-grained multi-threading. Note that this 100 numbers can be false because you have limited bandwidth. It might take more than 100 cycles if you have a lot of requests going to DRAM. But overall concept of fine-grained multi-threading, I stall, I switch, I stall, I switch. In this case, I can stall up to 100 cycles. I'm going to maintain 100 different threads in hardware so that I can switch all the time, right? This is going to look something like this. Thread 1 come in. This is cycle number 1, cycle number 2, cycle. This is thread 2, cycle number 3, thread 3, cycle number 4, thread 4, blah, 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 right? So that you can always switch to doing something useful. So what's the benefit of this? What's the benefit of this? So there's a question of what if there's so many memory accesses, then in that case, you ended up having to stall, right? You might have to stall, but this would allow more useful work by the processor because every single cycle, you're not wasting anything. You never stall. How about single thread performance? How much time do I need to finish one instruction for thread 1? A lot, right? So instead of 5 cycles, probably, right, if you do an add, you actually ended up using 100 cycles. So downside, really horrible single thread performance. Really horrible, like a lot worse, way worse. Don't ever do this, kind of worse. And you need extra logic to keep the thread context, right? So let's talk about GPU. Anyone hear about SIMD or SIMT, single instruction? Multiple data or multiple thread? What it really means is single instruction operate on a lot of data. Let me use this example. If I have a SIMD width of 8, it means that I'm gonna fetch an instruction. I'm gonna decode it. Apparently, that instruction works on 8 different pieces of data. It can be a vector add. I add 8 elements at the same time, so that's a SIMD instruction. Vector multiply. I'm gonna multiply 8 different things with another 8 different things so that I can write into 8 different results, right? What's the benefit of SIMD? Actually, it's the same data access because you're gonna end up doing the same amount of data access, but a lot more throughput, right? Because when you fetch and decode, somehow you're gonna do 100 operation at the same time instead of 1, or 2, or 32 instruction instead of 1, right? Yeah, things like ray tracing use SIMD. So a GPU is a combination of SIMD and fine-grained multithreading. And I'm gonna go through this in detail. So here's the GPU core. Now let's say you write OpenCL application or CUDA program, right? These are really, really, really highly parallel application. You're gonna have hundreds and thousands of threads. Basically, you're gonna end up with hundreds and thousands of threads. This is called a thread block. You have multiple thread block. Each row here, we call this a warp. A warp is a group of thread blocks. And your application is going to have multiple thread blocks. Basically, it can be 1,000 threads, 10,000 threads, even 1 million threads. They'll send the thread block to the GPU core. This is what we call simultaneous multiprocessor by NVIDIA. These are the GPU core. Each cycle, the warp will get forward to execution unit. What is execution unit? These are the ALU, the add, multiply. So what does this mean? One cycle, everything go to the ALU. So one cycle, how many operations? For this example, there are 8 ALUs. So one cycle, how many things you can do? So a warp is basically a collection of threads that would run together. Basically, it's a collection of multiple threads that in the cycle you run them together. And you basically distribute the thread blocks everywhere across all the GPU core. One quick caveat. NVIDIA keep calling the GPU having multiple CUDA core. CUDA core is it's not a real processor core. CUDA core is one execution unit. How many cores do I have? An actual cores look at the SM, simultaneous multiprocessor. So let me zoom in and go back to our 5-stage pipeline. Still remember this? Our old friend 5-stage pipeline with the fetch, decode, execute, memory, and write back, right? So here's a high-level overview of what's on the CPU side. So you have things like instruction cache. There was some questions about, hey, do we have instruction? Well, cache for the program because you have to fetch, right? Fetching at the memory takes a long time, so it makes sense to put instruction cache. Decoder, obviously you need to know what are you running. ALU, again, obviously you need to be able to do something. Load store unit, this is actually handling whenever you have to go to DRAM. And write back phase, basically register files and things like that, right? We talk about branch, you need branch prediction logic to predict if you're going to an if or else, right? You have fancy method to actually make the CPU even faster. These are things we haven't covered, but it's actually there on every single CPU to make sure you can run things in any order. You don't have to go von Neumann order, first line, second line, third line, fourth line. You can go first line, fourth line, third line, second line, and then fifth line. As long as there's no ordering data dependency issue, you will issue the instruction in any order. We call that out of order execution, and you require additional hardware to support it. You have a relatively large SRAM cache. What SRAM cache is for? So there's a question on the chat. Is a warp a subset of thread block? Yes, they are a subset of thread block. So what's the cache for? Come on, we talked about this for a long time. What was there for? For caching. For what? For latency. Make sure memory is fast, right? Memory access is fast. You have our old friend register files. Architecture of register files is the one programmers see. Basically, programmers see anything here. This is what the programmers see. And if you think about it, we add many components to make sure single thread performance is blazing fast. Really fast. Right? So many components are being added to the CPU to make sure single thread performance is awesome. Let's look at the GPU. If you look at the GPU, what's a common thing that we do in graphic operation? A lot of geometry calculation, right? To actually put things on your screen. A lot of them would be repeated operation. Add, multiply. Same operation. If I have to do the same operation, can I use SIMD? I can use SIMD, right? So if I'm a GPU designer, do I need the branch predictor logic? Well, I can take it out. I don't need fancy out of order scheduling. I'm gonna take it out. I see I have way more area on my chip. What am I gonna put in? Because I know I need to do a lot of the same operation. I'm gonna make the ALU a lot bigger. There's tons of adder, tons of multiplier. I'll take away. Oh, I need to maintain multiple threads. What does it mean? I need a lot of copy of register file. So your register will be huge because I have to run hundreds of threads at the same time. It means that I need to support that many threads. So your register file is gonna be huge, right? If my register file is huge, I don't have as much room for the cache. I'm gonna make it small. What does this do? It's a new design, right? It's a new design that I added so that I can run many things in parallel. I can run many things in parallel. And here's a normal compute operation. You run one instruction at a time, specifically one warp at a time. In a warp, there can be many operations in the thread, but each thread would run the same exact operation each cycle. It has to be an add because why? You have one decoder for 32 ALU. If you have one decoder for 32 ALU, can you differentiate between an add and multiply? No, right? So everything has to be an add, everything has to be a multiply, everything has to know ahead of time what do you have to do. There are different proposals to do like 2 add and 1 multiply or 4 add and 1 multiply. Depending on the architecture and what they do in the compiler, but the overall goal is one decoder, multiple ALU, right? So what's the benefit? You can run many operations, add in one cycle, right? So your throughput is gonna be sky high. Per one cycle, you're gonna do 32 adds, 64 adds, 1000 adds, right? But what if I need to go through my pipeline, right? How do I deal with stalling? So here's this. So let me actually give a cartoon example of 4 warp on a GPU. Each warp is 8 threads. This is GPU core. A box, this small box is a thread. And you look at the time. While the GPU is active, the GPU core would pick one of this warp, right? And put that in the pipeline. With fine-grained multi-threading, what happened next cycle? Basically, this is fine-grained multi-threading, but in a warp level. So what happened next cycle? You switch warp, right? You switch warp to avoid stalling. So the next cycle, you go warp C. The next cycle, you go warp B. The next cycle, you go warp A. Basically, it's you switch to another thread, but you are operating in the warp granularity. Basically, you execute an entire warp. So the next cycle, you switch to another one. So let's say warp A has a load and store. How many data access it generates? 8, right? So you're gonna generate 8 loads. It's gonna take a while to service those 8 loads. So what are the remaining options? You're gonna then rotate through DCB again, right? DC and B, DC and B. GPU becomes active at during this time. It's not stalling. It's still running something useful, right? See the benefit of having a GPU. Why this is really fast until everything is a load and store. That's when you actually have to wait. You have to wait, and GPU core is now not running anything until something comes back. When something comes back, it is become active again and you can resume execution. All right. So that's how GPU stall, right? That's how GPU stall. So let me ask you this question before we wrap up, because that's the last slides on how the GPU work. So let me go back to the question again. What's the benefit? Oops. 10 benefit. So high throughput, right? In one cycle, you do a lot of operation and you rarely stall. So what if, let me ask this what if question. What if you run single thread program on the GPU? What will happen here? I only have one thread, but I want to be fancy. I want to launch it on a GPU. What happened here? It's going to be extremely, extremely slow. It's going to be excruciatingly slow, right? So one of my last key message is that if you know how the GPU work in the future, don't always listen to NVIDIA salesmen who always claim that GPU is always awesome and fast. My research revolves around GPU, right? It's not like I hate GPU. I love GPU, but you need to know what they are for. If you have, so what kind of application would be fast on a GPU? Rendering, graphic, model training, graphical inference, right? Well, I think you mix two things in the same one word. SolidWorks, right? So what it does, we typically call this data parallel application. It means that I can parallelize operation on the data using the same operation again and again and again and again, right? What are the common traits of these applications? Same operation again and again and again, right? So this is going to be blazingly fast to run on the GPU. All right, are you with me so far? What about application would be really bad to run on a GPU? Yeah, things that even though you can parallelize them, it's not the same operation. That's going to be slow, right? Math operation can be fast. Math operation can be fast. Actually, there's a lot of operation in math that we can do in parallel. Machine learning is also really fast. Machine learning is matrix multiply. What do we know of matrix multiply? Are we doing a bunch of multiply and add in parallel? Right? So those are blazingly fast on a GPU. A single thread application would be slow on a GPU, right? So there are many things that in modern day computing that will be excruciatingly slow if you run it on a GPU. The GPU is not a silver bullet. That's my key message. It's not the silver bullet to every single problem, despite how much NVIDIA want to push this for you, right? There are things that are really good to run on a GPU, and I think that are really bad to run on a GPU. As a programmer, it's your job to know. It's your job to know. Now that I teach you how the GPU works, what's the trade-off? Hopefully, going forward, if you try to run things on a GPU and it becomes slow, you might have some insight, to be honest, like insight to either, hey, how do I make it fast? Right? How do I fully utilize the power of this GPU? Or how do I reprogram or even just optimize it on a CPU, right? Compression and decompression can be fast as well. Depending on how the algorithm works, right? So this can be also really fast. You, as long as you break down the program to make it data parallel, it's gonna be fast on the GPU. Right? I'm not saying it's not a powerful thing. It's a really extremely powerful thing, but you need to know how to use it, right? Every single tool demands knowledge and how to use it. Don't treat every single tool as a silver bullet. It's not one size fits all. And that applies to like many questions that you have to stumble upon in the world, right? And that's it for the class today. I hope you enjoy a lot of this unnecessary material that are not going through the exam, but hopefully fun to listen to. Uh, So there's a question. Then we want we get to the point that we have the mini specialized computer in every single computer that you buy. Anyone here own a mobile phone? What is in a mobile phone? We actually typically call a mobile phone system on chip. It's called system on chip, right? And with system on chip, you have the CPU and you have a lot of specially designed accelerators, specially designed hardware to process information. Why do we need it? So if you are trying to do a recording, let's say you have a karaoke session with your friends through the mobile phone app, right? Do you need to trigger the signal processing accelerator to process the voice and to process the sound? You do need one, right? What about video embedding and video encryption? You also might need another accelerator, special hardware to process those data. Camera, do you need a special hardware to process your camera feed? Your phone also, like new iPhone and I'm sure multiple Android phones, right, comes with a machine learning. What about they call neural processor? These are machine learning accelerators. It's designed to do a lot of matrix multiply, right? So these are special little piece of hardware being added to make your phone a lot faster, a lot more energy efficient. There's also things like the security chip from Apple, for example, but that would actually try to make sure your fingerprint ID and anything that has to do with privacy is is safe. Even the iOS will not be able to access it. It's actually handled by the chip, right? So these are several things that are being added on your mobile phone. So these days, if you own a phone, it's actually a bunch of cool uh, component that are being added on top of just the CPU and the GPU. And yes, I would agree that it would be sad to, in this day and age, if you need to have like online classes and things, uh, that you don't have these devices because it actually help your lifestyles, right? And I mean, I know for the fact that a lot of people cannot afford it, right? Yeah, I'm only a lecturer. Like I don't know a great solution. I don't. Even if I have a solution to that, I don't have the power to like apply the solution that I have in mind. All right. So that's it for the recording part. So let me stop the recorder here.